For the most part, I want you to just get down to basic probability and the basic trees for probability. We're going to talk about how many outcomes there are, what your sample space is, and I left a place on your notes to make a tree with me, so that it's important that you keep those notes handy. We're going to see how that tree diagram works to help find your probabilities. That's our goal today. And we're going to talk about the 3 types of probabilities soon, but today we're going to look at the theoretical parts. Your theoretical probabilities are probabilities that are set. They're not going to change. What you do when you flip a coin is your experimental probability, your empirical probability. If I flip a coin and I say, theoretically, heads should come up how much of the time? Half of the time I should get a head, half of the time I should get a tails. If I hand everybody in here a coin and I say flip this 10 times, will everybody get 5 heads and 5 tails? No, that's your experimental probability. Theoretically, we know over time, over the law of large numbers, over time, if we did this millions of times, we would approach that 1/2, that theoretical probability. What you guys will do when you do your experiments is called your experimental probability, or your empirical probability. That's different than your theoretical. We like to see it approach the theoretical with the more times we do this. So what we're going to look at is doing these experiments, finding out what possible things can come out of your experiments, which we call our sample space, and how many outcomes are involved in this. Now, your sample space, say I am tossing a die. How many sides does a die have on it? 6, yeah, your standard die. It has 6 sides. If I say how many outcomes there are, how many possible things can happen, how many possible outcomes are there? 6 possible outcomes, right? My sample space would be just this. I could get on die 1, 2, 3, 4, 5, 6. Theoretically, my probability of getting a 1 is what? 1 out of 6. Same thing with getting a 2, or getting a 3, or getting a 4, or getting a 5, or getting a 6. Theoretically, there's 6 possibilities, 1 out of 6. My event says, what are you asking me to do? Find the probability of getting a 2. Find the probability of getting more than 3. This is your event in here. This is what I want you to get out of that sample space. Now, a simple event is something that just yields one possible outcome. Tossing a die, getting a 1. Tossing a die, getting a 5. Tossing a die, getting more than 3 has more than one possible outcome. That is not a simple event. Okay. So those are the things we're going to look at. I'm really big on trees. So I left you a little space so that we can talk about your trees here. We're going to make a tree diagram for flipping a coin 3 times. From that, we're going to make the sample space. We're going to figure out how many outcomes we have. We're going to look at the probabilities on the tree as well as in your sample space so that you can see where they come from. I need you to be able to see these probabilities. And yet it sounds simple, but it's probably been a year or so since you had Algebra 2. Could be 2 years, 3 years. So maybe you forgot your probabilities. Now, when you flip a coin, how many outcomes are there? 2. Heads or tails, right? They both have a 1/2 chance. If I'm going to flip 3 coins, each one of them has 2 chances, 2 outcomes. So altogether, if I flip this coin 3 times using your counting principle, I should get 8 outcomes. 2 from the first coin, 2 from the second coin, 2 from the third coin. 2 times 2 times 2, I should get 8 outcomes altogether. Now, the easiest way to start your tree so that you don't end up with 2 completely separate tree trunks is with you. Start like this. Here's you. You flip one coin. What can you get? Heads, tails. Each one of these has a 1/2 chance of happening. Put this in your sample space. Okay, this is your first coin. Now, you're going to flip the coin again. If you got a heads the first time around, what can you get on your second coin? Heads or tails, either or. So again, heads or tails. And down here, heads or tails. Again, independently, they're independent flips. It doesn't matter what I flipped before. They're still 1/2, 1/2. If I flip a coin 100 times, and I get 100 heads in a row. On my next toss, what is the probability of getting the heads? 1 out of 2. It is still 1 out of 2. It's a darn lucky coin for me, but it's still 1 out of 2. So this was my second coin. Now I need to flip a third one, the third time. So if I had the heads on the first and the heads on the second, what could I possibly get on my third? Heads or tails. Again, they have a 1/2, 1/2 probability. Every time, heads or tails. So, there's your tree. Your outcomes are your last glimpse here. So I've got 1, 2, 3, 4, 5, 6, 7, 8 outcomes. Didn't we say we would get 8 outcomes? Your probabilities are on your tree as well. Each one of them had a 1/2 chance of happening. Each time it was a standard coin. To make our sample space, just follow your tree limbs. Heads, heads, heads. You have 3 things. Heads, heads, tails. Follow it all the way to the end. Heads, tails, heads. Get your sample space. Heads, tails, tails. Okay. Now, a good way to make your sample space is when you take a major branch change, just make a space, like cut it, or maybe start like a little bit down further, or start alongside of it. So we have tails, heads, heads. Tails, heads, tails. Tails, tails, heads. And tails, tails, tails. Now I realize these two are exactly the same in terms of 2 heads and a tails, but the order is different. So they're 2 separate outcomes. So again, do we have 8 outcomes from our tree? 8 possible outcomes. Now, in your tree, because we put your probabilities here, you're going to multiply these probabilities. Watch. 1/2 times 1/2 times 1/2 is what? 1/8. 1/2 times 1/2 times 1/2. Aren't these all equal chances of happening? Each one of them has 1/8 of a chance. So if I say, what is the probability of a tails, tails, tails? What do you tell me? Tails, 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 1/8. I look at my sample space. Out of 8 possibilities, one of them is all tails, tails, tails. So you can take your probabilities off of your tree, or you can take your probabilities off of your sample space. If it's something you're going to keep doing a lot, you're going to make a sample space. Like if I keep asking you like 5 of these things, what is the probability of 2 heads and a tail in any order? There's 8 possible outcomes. Let's count how many have 2 heads and a tail. 1, 2, 3. 3 out of 8. Or I can go to my tree. Here's 2 heads and a tail. That's 1/8. Here's 2 heads and a tail. That's 1/8. Here's 2 heads and a tail. That's 1/8. 1/8, 1/8, 1/8. Add them together. 3/8. All your probabilities, when you add down this way, have to add up to 1. Your total sample space has to add up to 1. An easy way to do this is off your outcome, your sample space. you have 8 possibilities. 8 is your bottom number. I know this sounds basic, but this always snags a lot of kids. If I say how many outcomes, then you get a whole number, like you get a regular number, like 8. If I say what is the probability of, you get a fraction, a decimal, a percent. Okay, a part of the number. So you have to remember that. All your probabilities will go from 0 to 1. Generally, we use a fraction in something like this that we're dealing with fractions. You can use your decimal, and then usually like with weather and stuff like that, it wouldn't be a really good thing to say, well, today there's a 3 out of 5 chance of rain. 3 out of 5, like, what does that mean? 3 days out of 5 days on one day? You know, how would I interpret that? So that's why weather is usually percent. Weather is a percentage thing. Okay, so here's your coin, and we flipped it 3 times. We got 8 outcomes, and we can see each outcome. From your outcome space, your sample space, what is the probability that I will get a heads on the first toss? One half. Doesn't that happen 1/2 of the time? And see how that was a nice way to break up your sample space? What is the probability that I will get a heads on the last toss? Still 1/2. Because what is the probability of getting a heads or tails? 1/2. Still 1/2. Okay? Still 1/2. What is the probability of getting 4 tails? Four tails. I want 4 tails in my 3 tosses. Can't get that. So what's my probability? 0. Good. Can't get that. It doesn't exist. 3 tosses. Can't get 4 tails.
Oh.
I gotcha. Gotcha. Okay. All right. So now, we're going to take this, and we're going to describe the sample space for tossing a coin and rolling a 6-sided die. How many possible outcomes can happen when you toss a coin? 2, and they are heads or tails. How many possible outcomes from your 6-sided die? 6, and they are 1 through 6. So your counting principle says 2 times 6 should give you 12 outcomes. I'm big on trees, guys. Trees really will break down all your probabilities if you're really struggling with, trying to get to the probability. So, start with you. Does it matter if I toss a coin first or I roll a die first?
No.
No, I'm a little crooked.
I was over there.
Yeah, I'm a little crooked there. So, let's toss the coin first. So what can I get on my coin toss? My coin toss. Heads or tails? What can I get when I roll my die? 1 through 6. Now, yes, this makes for a little bit of a crowded tree. So leave yourself enough room. So we had 1/2 probability on your toss, and your die gives you a 1/6. That's why we don't ask you to do too many of these things, like toss another die, toss another die. You'd have your sample space all like crowded up together. And I can't tell you how many times kids crowd them all together and they can't see how many they have. So this guy too, 1, 2, 3, 4, 5, 6. Again, 1/6 at a time. So the probability of getting a heads and a 1 is what? 1/2 times 1/6 is what? 1/12. And doesn't that make sense? Because shouldn't I have 12 of these? Shouldn't I have 12 outcomes? 2 times 6? Each one being 1/12. They each have to be equal. And 12 of 1/12 add up to what? 1. I want you to see that this all makes sense. Okay? From this, we could also make your sample space. I have a heads, a 1, a heads, a 2, a heads, a 3, heads 4, heads 5, heads 6. And I do the same with the tails. See the pattern? Okay, did I really need my tree? No, the tree doesn't hurt. How many outcomes do I have here? 12. So the bottom number of my probability is 12. So what is the probability that I toss a heads and a 6? 1 out of 12. What is the probability that I toss a heads and an even number? Out of 12. 3, 1, 2, 3. 3 out of 12. Okay, here's one. What is the probability that I toss a tail and a prime number?
4, 5, 2.
3. 3 out of 12.
Wait, what number?
I don't know, which number is prime?
What about 2?
2 is a prime, yes. 3 is a prime. 1 is not a prime.
What is that?
Because your definition of prime says it has 2 factors, 1 and itself. 1 only has 1 vector. 1. So 1 is not a prime. They catch you that on almost all the Regents questions that deal with prime numbers. Always get you on that. Whether it's a spinner or a die, they always get you on the prime numbers. Okay, so now, let's try. We have in your book, we have on page 131, we have a survey chart. We have 3 possible answers to the survey. There would be yes, no, and not sure. Okay? And they want us to make a sample space, giving the responses to the survey and the gender of the respondent. What could the gender be? Male or female? How many outcomes, or other, how many outcomes should fall in my sample space? Be Martian, alien, and she gets 6, right? 3 times 2. Okay, so how should I start? I have 3 responses, 2 of my genders. How should I start my tree? Make me. Okay, 2 lines, and they'll be male, female. What's their probability? 1/2, just like the heads and a tail. Now, how many responses to my survey? 3. So we've got a yes, we have a no, and rather than use the same no, I'm just going to put S for not sure. We have a yes, we have a no, we have a not sure. What are the probabilities for the respondents? How many do I have? 3. So each one has what probability of getting 1/3. Good. Now, multiply them across. What is 1/3 times 1/2? 1/6. All the way down. And how many do I have? So what should this total add up to? 1. Good. Total should be 1. Now, give me your sample space. So what should my sample space look like? Follow your tree limbs. M, Y, M, N, M, S. Let's take a break. Start with the other one. F, Y, F, N, F, S. Do we have 6 in our sample space? Each one has a 1/6 chance of happening. Okay. I want you to see the correlation between the probabilities on the tree and the probabilities that come out of your sample space. They are the same thing. So if I ask you what is the probability that a male responded either way, what would the probabilities be? 1/2. Isn't that 1/2 of my tree? Right? 1/2 of my outcomes? 1/2. What is the probability that a male responded yes or no? What is it? 2, 6. 6 is my bottom number. Yes or no? 2 out of 6. Okay? So you see how your sample space can help? Okay? If I use my tree, I could say male yes, 1/6. Male no, 1/6. 1/6, then 1/6, give me 2/6. Or 1/3 when you reduce it. Good? Okay, now, yeah, I know they're annoying, but believe me, when we get to do this and we get a little bit more tricky, everybody's going to say, how do I get that tree? Okay, now I want you to make me a chart. You're going to give a response to the survey. How many responses to that survey? How many responses did they list? 3. And instead of the male-female, they want you to now use a geographic location. And how many geographic locations do we have? 4. So how many outcomes? How many outcomes should we have? 12. So, your goal